Hello everyone, in this video we'll be solving problem 39 combination sum. The problem statement is we are given an array of distinct integers candidates and a target integer target. We need to return all unique combination of candidates where the sum of the chosen numbers is equal to target. In example number 1, the input given to us is 2, 3, 6 and 7 and the target is 7. There are two combinations of arrays which will give us the sum of 7. One is 2 to 7 and the other is 7. Please note that the number 2 is repeated twice, but in the input array candidates 2 only appears once. I hope you are able to understand the problem statement. Now let's switch to whiteboard and discuss how we can solve this problem. Let's use these input combinations to understand the solution. The best approach to solve this problem is to use backtracking, where we'll use DFS to iterate through all possible combinations and compare the total against the target, and if the value matches, we'll save the corresponding arrays into a collection, that is our output. This is a combination of backtracking and greedy approach, as we need to identify all the combination whose sum is equal to target. We'll start with the first element in the nums array. If we try to draw a graph using the first element as the root, its children will be all the elements in the input array. Now for each leg of the tree, we'll try to combine the values of the nodes and compare it against the target. If the sum matches the target, we have identified an subarray which will save it in the collection. For example, the leftmost leg contains 2 and 2 whose sum is 4. As 4 is not equal to target, we'll build one more level deeper with 2 as the root node. We'll repeat the same cycle for level 3 where we'll add all of the 2's which are the leftmost leg, compare the total against the target. We will try the same combination on other legs as well to compare the sum against the target. And once we have iterated through all the combinations, we'll try a different pair with 2 as the root node and 3 as the second node. The sum is 5 and from 3 we'll repeat the same cycle. So the next nodes available to us after 3 are 3, 7 and 6. As we have already identified all the combinations with 2's, we don't need to repeat that combination here because that will be duplicate. If we try to add 2 as one of the children to node 3, it will be a duplicate calculation because 2, 3, 2 or 2, 2, 3 is already covered in the first leg. So we'll try to avoid that by only using those numbers which are to the right side of the current number. Once we have identified all of the combinations with 2 as the parent node, we'll increment our pointer and then do the same with the next elements in the array as the parent node. So the next run would be with 3 as the parent node, following that will be 7 and then 6. With this solution, our time complexity is O of n raised to power t divided by n, where t is the target and n is the number of elements in the input array. The reason we are using t by n here is because it will help us identify how many levels deep we need to go to identify the combination that will give us the potential target. And the space complexity is going to be O of t by m, as it will help us identify how many maximum recursive depth we will have to go to identify all the combinations. One optimization we can do here is to first sort the array in ascending order and then apply the DFS approach. If the sum of the leg is already greater than the target, then there is no point in building another level because the sum is anyways going to grow further. By sorting, we can be sure if the sum is greater than the target, then we can stop any further recursion and start a new combination by backtracking. This optimization will not improve our theoretical time complexity, but it will certainly help in runtime. I hope you were able to understand the explanation. Let me show you how we can implement this using C#. Here is my C# solution. I start by sorting the input array into ascending order and then initialize my results variable. I'm then calling this helper method, which will recursively call itself using the DFS approach. In this helper method, I'm validating that the current index is less than the candidates.length to avoid getting index out of bound errors. I then create a temp sum variable, which is the sum of the current sum plus the current candidate that the index is pointing at. If the temp sum is greater than the target, it means we have already crossed that target, so we don't need to recursively call the method again. We stop the iteration and break out of the loop. If the target is equals to temp sum, means we found an subarray, so I'm saving that nums list. In the else block, I'm adding the current element to the nums list and then call the helper method again. After the recursive call is complete, I'm removing the nums element from the nums list again and then calling the helper method to try a different combination. This is where we are implementing the backtracking, where we do the certain operation by adding the element to the list and then remove it to try a different combination. Once all of the recursive loops are complete, we will return the results variable from the main method. This code, when submitted on LeetCode, beats 82% of the submissions in terms of runtime and 17% in terms of memory. Thank you for watching this video. I hope you were able to understand the explanation. The details to access the source code is available in the description below. Feel free to check that out, and I will see you in the next one. Thank you.